Hey everyone, and welcome to The Explainer. All right, let's jump right in. Today we are absolutely not doing a standard dry chemistry lesson. No way. Instead, we're diving into the awe-inspiring story of the universe's ultimate superstar atom, carbon. Seriously, this is a story of how a single, seemingly ordinary element completely dominates the entire world around us.
To really wrap our heads around this, let's start with a little mental exercise, directly from your textbook, Activity 4.1. I want you to just take a second and imagine compiling a list of 10 things you've used or consumed since you woke up this morning. You know, your toothbrush, the plate you ate your breakfast on, the food itself, your clothes, maybe the bicycle or bus you took to get here. Okay, now imagine sorting all those everyday items into columns, one for things made of metal, one for things made of glass or clay, and then a final column just labeled Others.
So, if you really look at that list you just made, your Others column is going to be absolutely massive. We're talking food, clothes, medicines, books, plastics. Almost everything in that giant column is based on one incredibly versatile element, carbon. In fact, all living structures, and yeah, that includes you and me, are entirely carbon-based.
Now here's where things get kind of wild. This creates a huge paradox. With carbon being the literal foundation of all living things and practically everything we use every day, you'd think the Earth would just be overflowing with it, right? Like it should be everywhere, but it's not. The Earth's crust contains a minuscule, tiny 0.02% of carbon in the form of minerals like carbonates, coal, and petroleum.
And honestly, it gets even crazier. Up in our atmosphere, carbon makes up just 0.03% in the form of carbon dioxide. So think about this for a second. We've got a massive mystery on our hands here. How does an element that is so incredibly rare in nature manage to absolutely, completely dominate the chemistry of life and industry?
Well, to solve that mystery, we just need to understand its underlying logic. Here's our roadmap for today. 1. The dilemma of 4. 2. The magic of covalent bonds. 3. Carbon's secret superpowers. 4. Flames in suit. 5. Saturated versus unsaturated chains. And finally, 6. Naming the carbon family.
All right, let's start with Section 1, the dilemma of 4. This is all about carbon's atomic conflict.
Everything you need to know about carbon comes down to its atomic number, which is 6. That means it has 2 electrons chilling in its inner shell and 4 hanging out in its outermost shell. Now, to reach a super-stable, happy, noble gas configuration, it urgently needs 8 in that outer shell. But here is the impossible dilemma it faces. On one hand, if carbon tries to gain 4 electrons to form a C4- anion, it totally fails. Why? Because a tiny nucleus with only 6 positive protons simply can't hold on to 10 total negative electrons. It just doesn't work. On the other hand, what if it tries to lose those 4 outer electrons to form a C4+ cation? Well, doing that requires a massive, literally impossible amount of energy to rip them all away. So it can't steal and it can't give away. What on earth is it supposed to do?
Section 2, the magic of covalent bonds.
Well, it shares. This is carbon's brilliant breakthrough. If it can't steal or lose electrons, it decides to just share its valence electrons with other atoms. Think of a carbon atom like a universal 4-peg Lego block. It's got 4 connection points, and it is more than happy to snap together with almost anything that will share an electron back.
So grab a mental whiteboard, and let's actually sketch out the simplest carbon compound step by step, methane. Step 1. Draw your carbon atom right in the middle and place 4 dots around it. Those are its 4 valence electrons. Step 2. Let's bring in 4 hydrogen atoms. Now, hydrogen has an atomic number of 1, right? So each hydrogen brings just 1 electron to the table. Step 3. Snap them all together. Each hydrogen shares its 1 electron with carbon, and carbon shares 1 of its electrons with each hydrogen.
And boom, here is the official textbook result. Carbon now gets to count 8 electrons all around it, giving it that highly desired, stable octet. And each hydrogen gets to count 2, totally satisfying their outer shells as well. This shared pair of electrons is what we call a covalent bond. And because these electrons are shared and no charged ions are formed in the process, covalent compounds have really strong bonds within the molecule itself, but pretty weak intermolecular forces between different molecules. That's why they generally have low melting and boiling points.
Moving right along to Section 3, carbon's secret superpowers.
So carbon's unique sharing ability actually unlocks some massive superpowers, primarily its tetravalency, having those 4 pegs to share, and our absolute hero word of the day, Catenation. Catenation is the unique ability of carbon to form stable bonds with other carbon atoms. And because the carbon atom is so small, its nucleus holds on to these shared electrons really tightly. This makes carbon-carbon bonds exceptionally strong. It literally allows carbon to build an almost infinite variety of structural skeletons, long straight chains, complex branch chains, or even closed circular rings. It's like the ultimate molecular building set.
And this perfectly illustrates just how powerful catenation really is. Both of these substances you see here are 100% pure carbon. They are what we call allotropes. On one side, we have diamond. Every single carbon atom is covalently bonded to 4 others in a super rigid 3D structure, creating literally the hardest natural substance known to humans. But just by arranging those exact same carbon atoms slightly differently, we get Buckminster Fullerene. The atoms form a shape that looks exactly like a football. Same exact atoms, completely different properties. Mind-blowing, right?
Let's look at Section 4, Flames and Soot, where we take this into the real world. So what actually happens when we release that stored chemical energy? Imagine taking a spatula and burning a few different carbon compounds, like naphthalene, camphor, and alcohol. If you place a metal plate right above the flame, you'll observe something really fascinating. Some carbon compounds burn completely, giving you a nice clean flame, but others produce this yellow, smoky flame and leave a massive black deposition of unburnt carbon, which we call soot, right on the plate. Your textbook's Activity 4.4 proves this by having you adjust the air hole on a Bunsen burner. If you restrict the oxygen supply, even a fuel that normally burns clean will suddenly produce a yellow, sooty flame. Why? Because of incomplete combustion. The carbon just doesn't have enough oxygen to fully react.
Next up, Section 5, Saturated versus Unsaturated Chain Types.
That burning behavior we just talked about, it actually connects perfectly to how carbon chains use those chemical Lego pegs. Let's do another quick mental whiteboard sketch and build ethane, which has 2 carbon atoms. Step 1. Link the 2 carbon atoms together with a single covalent bond. Step 2. Look at what's left. Each carbon used one of its pegs to hold hands with the other, so they each have 3 valencies left. Let's satisfy them by bringing in a total of 6 hydrogen atoms. Step 3. Always check the math. Does every carbon have 4 bonds total? Yep, perfect.
And here is that step-by-step formation visualized for you. Because all the carbon atoms in this molecule are connected by only single bonds, we call this a saturated compound. But what if we wanted to build ethene, which only has 4 hydrogens available in total? Uh-oh, we run out of hydrogens. To satisfy that unbreakable rule of 4, the 2 carbon atoms just have to share 2 pairs of electrons with each other, creating a double bond. Whenever carbon compounds have double or triple bonds between the carbons, we call them unsaturated compounds. Simple as that. And finally, Section 6, Naming the carbon family. Let's decode the nomenclature. Okay, with literally millions of possible compounds out there forming chains and rings, scientists desperately needed a universal language to keep track of them all. And I promise you, you can name almost any compound just by looking at its structure. In what we call a homologous series, the carbon chain is basically just the skeleton. But a specific functional group, often featuring a friendly heteroatom like oxygen or a halogen, swaps in and replaces a hydrogen. This group dictates all the chemical properties. And the name? It just acts like a simple code. If you see a halogen attached, you add a prefix, like chloro. So a 3-carbon chain with chlorine just becomes chloropropane. If an alcohol group is attached, you add the suffix -ol, making it propanol. Aldehydes end in -al for propanal, ketones end in -one for propanone, and carboxylic acids end in -oic acid for propanoic acid. See? It turns what looks like scary pure memorization into predictable, beautiful logic. Now, here's a quick fun piece of history for you. For a really long time, people actually thought these amazing organic compounds could only be created by living systems. They believed there was some mystical vital force required to make them, but in 1828, a scientist named Friedrich Wöhler completely crushed this theory. He prepared urea purely from an inorganic compound, ammonium cyanate, right in his lab. It proved once and for all that organic compounds are just pure, understandable chemistry, governed by the totally predictable rules of covalent bonding and catenation that we just learned. So the next time you look around at your clothes, your food, or even your own hands, remember the incredible journey of carbon. By simply refusing to give up or steal electrons and choosing to share instead, it unlocked the ability to build the entire universe as we know it. And honestly, it makes you wonder, if carbon can build life itself out of just 4 tiny bonds, what else is hiding in the periodic table? Stay curious, keep exploring, and we'll see you on the next explainer.
Hey there, and welcome to this explainer. Today, we're doing something really cool. We are going to bridge the gap between the visible, everyday world, things like the flames on your stove and the foam in your sink, and the invisible, whiteboard-level molecular makeovers of carbon. If you're trying to wrap your head around how atoms rearrange themselves to create everything from car fuel to the soap you use to wash your hands, you are absolutely in the right place. So let's jump right in.
Here's a quick look at our roadmap. We are going to cover combustion and fuels, carbon's molecular makeovers, the story of ethanol, ethanoic acid, and finally, how soaps clean dirt.
All right, Section 1, Combustion, Flames and Fuels. Let's get started.
Imagine we're right in the lab doing activities 4.3 and 4.4. We take some carbon compounds, things like naphthalene, camphor, and alcohol, put them on a spatula, and bring them right to a flame. If you adjust your Bunsen burner, you'll see a pretty striking difference. Saturated hydrocarbons generally give this beautiful, incredibly clean blue flame, but the unsaturated ones, they burn of the bright yellow flame and kick off a ton of black, sooty smoke, like it'll instantly coat a metal plate if you hold it above the flame. And this all just comes down to the proportion of carbon and how completely it's able to react with oxygen in the air.
Now, that brings us to a really fun question. Have you ever just paused and thought about why a candle produces a bright yellow dancing flame, but the coal or charcoal in a barbecue pit sometimes just glows red hot without any flame at all?
Well, it turns out a luminous flame is only produced when gaseous substances burn. When you light solid carbon, like wood or charcoal, it only has a flame at the very beginning while its volatile gaseous substances vaporize and burn off. Once those are totally gone, the remaining solid carbon just glows red hot. Actually, those glowing colors are a characteristic property of the elements themselves. For example, if you heat a copper wire in a flame, you'll see it turn a completely different, very distinct color.
And speaking of carbon fuels, I love this quote because it brilliantly illustrates how our massive fossil fuel reserves were formed. Millions of years ago, tiny plants and animals died in the sea, were covered by silt, and under immense pressure and bacterial action, they turned into oil and gas. These fuels seeped into porous rocks and got trapped, literally just like water in a sponge, waiting millions of years deep underground for us to find them.
Moving on to Section 2, Carbon's molecular makeovers. Okay, let's grab our mental magnifying glass and zoom in like a million times. Walking through activity 4.5, we take some ethanol, warm it up gently, and then carefully drop in a bright pink 5% solution of alkaline potassium permanganate. At first, an amazing thing happens. The pink color completely disappears the moment it hits the ethanol. But as we keep adding excess drops, the pink color eventually persists. Why? Well, it's because that pink chemical is actually being consumed to transform the ethanol.
Let's sketch out these bombs on our virtual whiteboard for a second. Remember the law of conservation of mass from back in Chapter 1? It's exactly like a balanced scale. Atoms don't just vanish into thin air, they rearrange. In this reaction, the potassium permanganate is acting as an oxidizing agent. It is literally forcing a brand new oxygen atom into the ethanol molecule structure. Once all the ethanol has been successfully converted into ethanoic acid, the reaction has to stop. And that is exactly why that excess pink color from the permanganate finally sticks around.
But carbon doesn't just do oxidation. Oh no, it also undergoes addition reactions. Imagine long, unsaturated carbon chains in liquid vegetable oils. By using a nickel catalyst, which is just a substance that speeds up a reaction without actually getting consumed itself, we can force hydrogen atoms to literally add on to the double bonds. This turns that liquid oil into solid saturated fat. Or look at substitution reactions. If you mix methane and chlorine in the presence of sunlight, the sun provides the energy for the highly aggressive chlorine atoms to systematically knock off and substitute the hydrogen atoms one by one. It's like a molecular game of musical chairs.
Section 3, the story of ethanol, a very famous commercial compound.
So ethanol is a pretty spectacular solvent. It's the active ingredient in everything from cough syrups to tonics. Let's imagine performing a live demonstration of activity 4.6. You take absolute alcohol, which is just pure ethanol, and drop in a tiny rice-sized piece of highly reactive sodium metal. Instantly, something starts bubbling furiously inside that test tube. What exactly is that gas?
Well, those bubbles are pure hydrogen gas. The sodium reacts with the ethanol to form a compound called sodium ethoxide, and it releases hydrogen in the process. And ethanol has another really cool trick up its sleeve. If you heat it to 443 Kelvin with excess concentrated sulfuric acid, the acid acts like a molecular thief. It forcefully dehydrates the ethanol, literally stealing the components of water, H2O, right out of the molecule. What's left behind is an unsaturated hydrocarbon called ethene. We do need to be incredibly careful with alcohols, though. Biologically, consuming ethanol depresses the central nervous system, which slows down your coordination and judgment. However, its close cousin, methanol, is absolutely lethal. Inside the liver, methanol oxidizes into methanal, which rapidly reacts with your cells. It literally coagulates your cellular protoplasm in the exact same way that boiling heat coagulates the protein in an egg. It also directly attacks the optic nerve, causing total blindness. This is exactly why industrial ethanol is deliberately denatured by mixing in methanol and blue dye, just to make it entirely obviously unfit for drinking. All right, moving to Section 4, exploring ethanoic acid. Commonly known as acetic acid, this compound brings us to one of the most fragrant, pleasant reactions in all of chemistry. Let's walk step by step through activity 4.8. We take 1 milliliter of our old friend ethanol and mix it with 1 milliliter of glacial acetic acid. Then we add a few drops of our catalyst, concentrated sulfuric acid, and warm the test tube very gently in a water bath. Finally, we pour this whole mixture into a beaker of water and waft the scent towards our nose. And that incredibly sweet, fruity smell rising from the beaker, that perfectly illustrates esterification. We just created a brand new compound called an ester right before our eyes, simply by bonding the ethanoic acid and the ethanol together. Because they smell so wonderful, esters are super popular and widely used to make perfumes and artificial flavoring agents.
Now, despite being able to make sweet-smelling perfumes, ethanoic acid is, at the end of the day, still an acid. Just to prove that it acts like the mineral acids you studied in earlier chapters, it will happily react with a strong base like sodium hydroxide. In a classic neutralization reaction, they completely cancel each other out to form a salt, in this case, sodium acetate and water.
Finally, Section 5, how soaps clean dirt. Let's talk about micelles. Let's zoom back out to the macro world to solve a mystery you've probably wondered about every single day at the kitchen sink. Think about activity 4.10. If you take a test tube of water, add cooking oil, and shake it vigorously, what happens? They stubbornly, immediately separate into two completely different layers. Oil and water simply do not mix. But if you add just a few drops of soap solution to a second test tube and shake it, suddenly they stay perfectly mixed together in this cloudy emulsion. How exactly is this molecular magic happening? The answer is a tiny structure called a micelle. Soap molecules are incredible. They basically have two ends. One end is a long hydrocarbon tail that is hydrophobic, meaning it absolutely hates water, but it loves oil. The other end is ionic and hydrophilic, meaning it loves water. So when you put soap in dirty water, these molecules arrange themselves into tiny spheres. All the water-hating tails point inward, grabbing and trapping the oily dirt in the center, while the water-loving heads point outward toward the water. This effectively suspends the oil in the water, allowing the whole greasy mess to just be easily rinsed down the drain. So let's connect all of this right back to your daily life. From the complex micelles tearing dirt apart in our washing machines, to cleaner ethanol fuels derived from fermented sugarcane, to the industrial hydrogenation that creates the solid fats we cook with, carbon's unique ability to chain together and react is literally the absolute foundation of our modern world. You've just mastered the secret life of carbon, from the macro world of roaring flames all the way down to the atomic bonds of a microscopic micelle. So the next time you strike a match to light a stove or scrub your hands with soap at the sink, ask yourself, what other hidden carbon chains are quietly shaping your reality right now? Keep questioning, keep visualizing those bonds, and I'll see you in the next explainer.
All right, 10th Standard Warriors, welcome to your Chapter 4 Explainer. Today we're doing something a little different. Instead of just reading the textbook, we're going to step directly into the shoes of a Karnataka SSLC board evaluator. We're cracking open Chapter 4, Carbon and its Compounds, and I'm going to show you exactly how to secure every single possible mark in this critical chemistry chapter. We are hunting for those hidden half marks and avoiding the traps that catch out thousands of students every single year.
So here's our exact blueprint for this explainer. We'll be hitting the carbon bonding trap, structural formulas, saturated versus unsaturated compounds, high-yield chemical reactions, and finishing off with a masterclass on the soap micelle. Let's get into it.
Okay, Section 1, the carbon bonding trap. This is an absolute favorite for the examiners, a classic 2-mark conceptual trap.
They're going to ask you this directly. Why doesn't carbon just form C4+ cations or C4- anions? Now, you already know carbon has a tetravalency, right? But to get the full 2 marks, you absolutely must hit 2 very specific keywords the evaluators are hunting for on their scoring keys.
Listen closely. Do not write a long, rambling paragraph here. Give the examiner these 2 precise bullet points for a clean 1+1 mark split. For the C4- anion trap, you gotta write that it's difficult for the nucleus with 6 protons to hold on to 10 electrons. Bam, that is exactly 1 mark. And for the C4+ cation trap, you must state that it requires a large amount of energy to remove 4 electrons. Lock those phrases into your memory, guys.
Moving right along to Section 2, Master Structural Formulas. Let's look at where students needlessly leave half marks on the table. When you're asked to draw N-butane or isobutane, I want you to imagine drawing your carbon chain first. The golden rule here, tetravalency. Every single carbon atom must have exactly 4 lines, 4 single bonds connecting to it. If you miss just 1 single hydrogen bond or add an extra one by accident, you literally lose the mark. Count them out in your head. 1, 2, 3, 4 for every single C on your paper.
Now, what's really interesting is how examiners test cyclic structures. Take cyclohexane. The formula is C6H12, and man, this ring structure absolutely traps students. They'll draw the carbon hexagon perfectly, but completely forget that each carbon only needs 2 hydrogens to satisfy that tetravalency. You really have to count your hydrogen bonds carefully here to secure that mark.
And for propanoic acid, the most common mistake is missing the exact structure of the carboxylic acid functional group. You absolutely must show the carbon double bonded to the oxygen and single bonded to the OH group. Lock that specific arrangement in for your full marks. Whatever you do, don't rush drawing the functional groups.
All right, Section 3, saturated versus unsaturated. Get ready for a guaranteed analytical difference question. You need to memorize this exact grid. It is pulled straight from the official evaluation key. If they ask for differences, you write this table exactly as it is. And here's a high-yield memory trick to help you out under exam pressure. Just remember the rule of S's. Saturated equals single bonds equals substitution reactions. It's that simple. Unsaturated compounds, on the other hand, have double or triple bonds. They're way more reactive. They undergo addition reactions. And importantly, they burn with a yellow flame with black smoke, which is totally different from the clean flame of those saturated compounds.
Next up, Section 4, high-yield chemical reactions. These are the equations that separate the good papers from the perfect papers.
When writing the esterification equation, so many students just write down the reactants, ethanoic acid and ethanol, and the ester product, but they completely forget the crucial conditions and the byproducts. You need every single one of those details for a perfect score.
You've got to think like an evaluator here. Writing the phrase sweet-smelling substance and mentioning the acid catalyst right above the reaction arrow tells the examiner you actually know the chemistry. You're not just memorizing letters. They literally scan the page for these exact words. So give it to them. It's a guaranteed half mark.
Also, keep a close eye on this reaction for your 2-mark balanced equations. When ethanoic acid reacts with sodium carbonate, do not forget the 2 coefficient in front of both ethanoic acid and sodium acetate. It is a classic balancing trap that catches people out every year. Oh, and also note that this reaction is easily identifiable by the rapid evolution of carbon dioxide gas.
Finally, Section 5, the SOAP Micelle Masterclass. This right here is the heavyweight 4-mark application question. You need to write out these exact 4 steps to claim your 4 marks. It's a precise formula. You literally get 1 mark just for mentioning the ionic or hydrophilic end interacting with water and the carbon chain interacting with oil. You get your 2nd mark for stating this forms a micelle and creates an emulsion. And the final mark is for explaining that the micelle pulls the dirt out into the water. Keep it structured exactly like this, step by step. And here is the ultimate follow-up trap: hard water. If they ask why we need large amounts of soap in hard water, immediately state that hard water contains calcium and magnesium salts. The soap reacts with these specific salts to form scum, which is an insoluble precipitate. Why are detergents better? Well, because they simply do not form these insoluble precipitates with calcium and magnesium ions. Boom, full marks, right there.
So, you've got the blueprint, and you know exactly where the marks are hidden.
But as you go into that exam hall, ask yourself, if carbon's incredibly versatile bonding can create literally everything from the graphite in your pencil to the DNA in your very cells, what other incredible molecular secrets are waiting to be unlocked in your future? Review these points, ace your exam, and keep questioning the chemistry of the world around you.